Good morning. So we start from the point where we left last week. You remember it was my intention to show you a short movie that describes an experiment of electron diffraction. The experiment shows that if you launch a number of electrons, one after the other, through a couple of very narrow slits, and then you detect the electrons on the other side of the screen where the two slits are, and the screen and the detection method is another screen in which there is a film that records the positions of the impinging electrons. The outcome of the experiment is that the distribution of the electron is such that a diffraction pattern becomes visible, very similar to that that is obtained by performing the same experiment using monochromatic light. For this reason, the experiment is called the experiment of diffraction of electrons. If you look at the textbooks, this experiment goes under the name of Davison and Gelmel experiment, okay? But in fact, Davison and Gelmel performed a series of experiments that we shall see after watching the movie. But these experiments were different. They actually ended up with this conclusion, okay, that there is a phenomenon of diffraction. But the experiment was not carried out in the way that is presented in textbooks. The original experiment by Davison and Gelmel was carried out in 1926. And at that time, performing the experiment with the two slits was technically impossible. So they were doing something different. There is a claim that the experiment with the two slits has been done first in the 80s, in the late 80s in Japan, but actually this is not true either. The experiment was done in Bologna for the first time in the 70s in a laboratory of the National Council of Research, and the movie was issued by that laboratory. The movie has subtitles in English, okay, so now I will try to start it, hope with better luck than last Friday. In any case, even if I succeeded last Friday to show you the movie, it would be too long, okay? So on Friday, there was no time actually to watch it completely. So let me try to share the desktop. And now you should see something dark with something written in Italian. Let me check whether the audio of the computer is shared. It should be also shared. Okay, so I'm going to start the movie now. The length, the duration of the movie is about 24 minutes. The year was 1974, and the movie was redone in 1976 at the CNR in a laboratory in Bologna. And I shall also post the website.
Maggio 2002. Sulla rivista inglese Physics World, Robert Crease, professore di filosofia della scienza all'Università Stony Brook di New York, lancia un sondaggio. Qual è il più bell'esperimento di fisica di tutti i tempi? Oltre 200 lettori rispondono. Al terzo posto si classifica l'esperimento di Robert Millikan per misurare la carica dell'elettrone. Al secondo, l'esperimento di Galileo Galilei per determinare la legge di caduta dei corpi. E al primo posto, l'esperimento della doppia fenditura di Young applicato all'interferenza del singolo elettrone, realizzato nel 1974 da un gruppo di ricercatori italiani di Bologna: Pier Giorgio Merli, Gianfranco Missiroli e Giulio Pozzi. L'esperimento consiste nello sparare elettroni, uno alla volta, verso un rivelatore, davanti al quale è posto uno schermo con due sottilissime fenditure. Sul rivelatore compaiono dei puntini luminosi. Questi corrispondono all'impatto degli elettroni sul rivelatore, come se essi fossero piccolissime particelle. Con il passare del tempo, però, i puntini non formano una figura a due strisce, come farebbero delle normali particelle, bensì una figura a molte strisce, una figura, cioè, di interferenza, come farebbero le onde. Questo comportamento duplice degli elettroni è uno degli aspetti più sorprendenti previsti dalla meccanica quantistica. Questo esperimento fu pensato per la prima volta da Albert Einstein durante il famoso congresso Solvay del 1927 e divenne oggetto di una disputa teorica con Niels Bohr, ma tutti per moltissimo tempo lo ritennero tecnicamente troppo difficile da realizzare. Ancora nel 1963, il fisico americano e premio Nobel Richard Feynman scriveva: «Vi avvertiamo subito di non cercare di montare questo esperimento. Il guaio sta nel fatto che per rivelare gli effetti che interessano, l'apparato dovrebbe essere costruito su una scala talmente piccola da rendere impossibile la cosa». E dunque, come hanno potuto i ricercatori bolognesi, dopo poco più di 10 anni, smentire le previsioni di Feynman? Secondo il filosofo Karl Popper, esiste uno sfondo culturale che influenza lo sviluppo della scienza. In ogni epoca storica, le domande importanti per il progresso della conoscenza sono in parte il frutto della cultura del tempo e del luogo. Bologna, conosciuta per le torri, la buona cucina e i 38 chilometri di portici, è una città che vanta solide tradizioni democratiche e di buon governo. Medaglia d'oro della Resistenza per il contributo dato dalla sua gente alla guerra di liberazione, Bologna è una città fondamentalmente prospera, che manifesta e alimenta il suo benessere con il ricco commercio del centro e l'operosità intelligente della sua media e piccola industria. Ma Bologna è soprattutto città di eccellenti tradizioni scientifiche e culturali. Qui ha sede la più antica università europea, fondata nel 1088. L'università è luogo in cui la ricerca si sviluppa indipendentemente da ogni altro potere, recita la Costitutio Habitat promulgata nel 1158 da Federico I Barbarossa. E questa indipendenza dai poteri l'ha portata a partecipare con idee nuove e spesso radicali alle grandi rivoluzioni scientifiche. A Bologna, tra il 1495 e il 1500, Niccolò Copernico iniziò le sue osservazioni astronomiche, preludio alla formulazione del sistema eliocentrico. Qui, nel 1781, Luigi Galvani scoprì il fenomeno dell'elettricità animale. Qui insegnò Laura Bassi, la prima donna ad ottenere nel 1776 una cattedra di fisica sperimentale. Qui Augusto Righi, alla fine dell'Ottocento, aprì la strada alle applicazioni dell'elettromagnetismo. Qui, infine, tra fine Ottocento e inizio del Novecento, Guglielmo Marconi inventò le comunicazioni via radio. Anche l'esplorazione del mondo microscopico, che porterà all'esperimento più bello, ha a Bologna illustri precursori. Nel Seicento, infatti, periodo aureo della medicina bolognese, il microscopio diventò lo strumento principale delle ricerche anatomiche di Marcello Malpighi. E sempre nel Seicento, Bologna divenne protagonista del dibattito sulla natura della luce. Fu qui che il padre gesuita Francesco Maria Grimaldi scoprì il fenomeno della diffrazione. Questa scoperta avvalorò l'ipotesi che la luce fosse un'onda, in contrasto con l'idea di Newton che essa fosse costituita da uno sciame di microscopiche particelle. Tra la fine degli anni 60 e l'inizio degli anni 70 del secolo scorso, Bologna manifesta ancora il suo ruolo di terreno fertile per lo sviluppo della ricerca scientifica.
Fu un momento di straordinaria bellezza perché il lavoro dei ricercatori era animato dalla speranza che la ricerca scientifica potesse veramente incidere nel fenomeno di crescita del paese.
Oggi si parla di crisi dell'intellettuale. Allora la situazione era capovolta, gli intellettuali si sentivano organici alla società, sui giornali e sui libri. Scrivevano Italo Calvino, scrivevano Pierpaolo Pasolini, quindi una vivacità intellettuale che era poi figlia del 68, preparato da un lungo periodo di lavoro e di scrittura.
Questo momento di straordinario fervore si rifletteva anche nella vita dei ricercatori. L'impresa, la costruzione dell'AMEL e degli altri laboratori, poi istituti del CNR, sono un episodio della parte più bella della storia recente di questo paese, insomma. Quando si puntava sulla scienza, quando si investiva sulla conoscenza scientifica, non soltanto a livello pubblico, ma anche a livello privato.
E nel nostro piccolo cosmo la situazione rifletteva in fondo questo mondo che era intorno a noi. Noi avevamo un istituto che era pensato congiuntamente tra università e CNR. 50% circa del nostro personale era personale universitario. Quindi per noi era naturale, diciamo, questa fertilizzazione. Non avevamo antagonismi, ma avevamo appunto, come vi dicevo, pensavamo congiuntamente a queste esperienze.
In questo contesto, grazie alla convergenza di fattori umani e tecnici, maturarono le condizioni che portarono alla realizzazione dell'esperimento di interferenza dell'elettrone singolo. Merli, Missiroli e Pozzi si incontrarono intorno al 1970 all'Istituto di Fisica dell'Università di Bologna, nel laboratorio di microscopia elettronica del professor Ugo Valdré. Qui iniziò il percorso che li avrebbe portati, di lì a pochi anni, a realizzare l'esperimento più bello della fisica, rimasto fino a quel momento puro esperimento mentale.
Nel gruppo eravamo 2 ragazzi giovani assetati di ricerca scientifica, io e Pier Giorgio Merli, e una persona un po' più anziana, Gianfranco Missiroli, che era docente di sperimentazioni fisiche in di questo dipartimento e che è stato proprio il nostro docente.
Il contesto culturale in cui io, Possi e Merli portavamo avanti le nostre ricerche era il medesimo, all'interno di un laboratorio di microscopia elettronica. Continuamente facevamo esperienze utilizzando dei concetti molto importanti per quanto riguardava gli elettroni. Hanno un comportamento ondulatorio, hanno una certa massa e hanno una certa carica. Non sono come la luce, però il fatto che avessero un comportamento ondulatorio davano origine a degli effetti che erano gli stessi che si potevano vedere nella luce: diffrazione e interferenza. Sarebbe stata una cosa bellissima per tutti gli studenti di fisica del primo e del secondo anno che, dopo aver fatto un'esperienza di interferenza o di diffrazione della luce con laser, si sarebbero potuti portare al microscopio elettronico e dire: vedete, noi non utilizziamo più onde elettromagnetiche, utilizziamo delle particelle che hanno una massa m ben definita, uguale per tutti. Millikan vi dice qual era la carica e qual era la massa di questa particella. Poi c'è stato un altro, un francese, che ha detto che sì, ma queste particelle avrebbero avuto anche una lunghezza d'onda.
La mia collaborazione con Franco è iniziata ribaltando completamente quelli che erano i canoni usuali in cui si faceva ricerca e si utilizzavano i sottoprodotti per la didattica, in quanto siamo partiti da un'esperienza didattica e su quella abbiamo costruito un'attività di ricerca che sto portando avanti ancora in questi giorni.
L'esperimento che a detta di Feynman conteneva tutti i misteri della meccanica quantistica, esercitava un notevole fascino sui ricercatori bolognesi.
Sia io che Giorgio, come studenti un po' più giovani, eravamo affascinati dalla meccanica quantistica, dai problemi di interpretazione che essa presentava, ed eravamo tutti e 3 consci che questi problemi intervenivano in maniera cruciale nella esperienza di interferenza di elettroni.
Per fare l'esperimento bisognava risolvere le difficoltà tecniche previste da Feynman. In particolare occorreva realizzare i 3 componenti chiave dell'esperimento mentale: la sorgente di elettroni in grado di emetterne uno solo alla volta, il dispositivo per farli interferire, le fenditure, e il rivelatore in grado di evidenziare l'arrivo di ogni singolo elettrone. A Bologna si pensò di modificare un microscopio elettronico. Questo strumento era stato inventato nel 1931 dai tedeschi Ernst Ruska e Max Knoll per vedere dettagli estremamente piccoli della materia. Con opportune modifiche, esso poteva diventare un laboratorio per studiare le proprietà fondamentali degli elettroni stessi. Come primo componente per l'esperimento fu quindi utilizzata la sorgente di elettroni del microscopio elettronico.
Per noi il fatto di modificare lo strumento era qualche cosa di completamente naturale e proveniva dall'attività del professor Valdré, il quale nell'arco delle sue ricerche proprio costruiva, pensava la zona portacampioni come un piccolo laboratorio nel quale eseguire esperienze di crescita, di sottoporre i campioni a stress meccanico, stress termico e così via.
Il secondo componente, ovvero un dispositivo che consenta di far interferire gli elettroni, era stato inventato negli anni 50 da 2 ricercatori tedeschi, Möllenstedt e Dücker, dell'Università di Tubinga. Si tratta del cosiddetto biprisma elettronico, costituito da un filo molto sottile, conduttore di elettricità, collegato ad una sorgente di potenziale, in modo da generare un campo elettrico. Gli elettroni, la cui direzione di volo è perpendicolare al filo, sono deviati dal campo elettrico. Si viene così a creare una zona in cui gli elettroni che passano da una parte e quelli che passano dall'altra del filo si sovrappongono. È in questa zona di sovrapposizione che si realizza il fenomeno dell'interferenza. Tutto avviene come se essi provenissero da due sorgenti virtuali distinte, che funzionano come le due fenditure dell'esperimento mentale. La principale difficoltà fu quella di realizzare il filo, estremamente sottile, del biprisma.
Questo filo può essere procurato in diversi modi. Ad esempio, i francesi utilizzavano un filo di ragno e per questo mi ricordo che anche noi andammo qui nel giardino del Dipartimento a cercare dei ragni e farli e raccogliere la loro tela, però da noi non ha funzionato così bene come in Francia. In genere i ricercatori tedeschi utilizzavano quarzo, per il quale serve una fiamma ossiacetilenica, ma noi non l'avevamo e allora molto semplicemente abbiamo preso della silice, l'abbiamo fusa e tirata, evaporato sopra cromo e oro per creare uno strato metallico conduttore e proprio così come mostrato nel film, ma da persone molto più esperte con le mani più ferme, adagiare questo filo sul dispositivo, incollarlo e fare l'esperienza.
Con la collaborazione di Oriano Donati prima e di Giorgio Matteucci in seguito, venne realizzato il filo e con esso un modello di biprisma che poteva essere utilizzato nel microscopio elettronico, inserendolo dove normalmente viene posto il campione di materia da analizzare. Il terzo componente necessario, ovvero un rivelatore tanto sensibile da evidenziare il segnale prodotto dall'arrivo di ogni singolo elettrone, fu presentato nel 1970 ad Erice durante un corso di microscopia elettronica da Hermann, un ricercatore tedesco che lavorava alla Siemens, prima azienda al mondo che costruì e commercializzò i microscopi elettronici. Merli e Pozzi erano presenti a quel corso e da lì ebbe origine l'idea di utilizzare quel rivelatore per completare l'esperimento di interferenza dell'elettrone singolo.
Una volta che abbiamo cominciato a fare le esperienze di interferometria, è saltato fuori che il famoso rivelatore di immagini di elettrone singolo era stato acquistato da un gruppo di Milano, dal professor Bairati. E a questo punto tutti i fili si sono in un certo senso ricongiunti e qui Giorgio Merli, dando mostra di una attività manageriale di grande classe, telefonò proprio a Milano per avere la possibilità di fare l'esperienza dell'arrivo del singolo elettrone nella figura di interferenza.
Le immagini del monitor mostrarono finalmente i puntini che, accumulandosi, formavano le strisce di interferenza.
La meccanica quantistica ormai aveva ottenuto tanti e tali successi da rendere estremamente difficile dubitare del risultato di questa esperienza, però stranamente nessuno l'aveva fatta e noi ci rendevamo conto di essere stati i primi. 15 anni dopo il nostro esperimento, il gruppo di Tonomura lo ha ripetuto con strumentazione migliorata e in quel caso il nostro lavoro non era citato. La cosa si è ripetuta quando l'esperimento è stato classificato come esperimento più bello dalla rivista Physics World, in quanto l'editore della rivista ha attribuito il successo di questo esperimento proprio al gruppo di Tonomura, dimenticandoci totalmente. Prima che noi scrivessimo una lettera di correzione al direttore, siamo stati preceduti da colleghi ricercatori, in particolare John Steeds
di Bristol, il quale, conoscendo il film e conoscendo la nostra attività, ha provveduto a riportare la storia, diciamo, nei binari di correttezza e a far sì che la priorità dell'esperimento venisse attribuita al nostro gruppo.
L'idea poi di fare un film complessivo da questo materiale che avevamo ci venne proprio spontaneamente dal fatto che noi avevamo già un'attività iniziale, embrionale di cinematografia scientifica nell'istituto. Già Giorgio e Lucio Morettini avevano lavorato insieme a Milano per riprese sulla microscopia elettronica e quindi l'idea di organizzare attorno all'esperimento un film complessivo che illustrasse questi esperimenti in relazione agli altri fenomeni di interferenza ci appariva del tutto naturale e congeniale.
Di per sé l'esperimento aveva importanza se veniva visualizzato non con una sequenza di pochi fotogrammi come si possono riportare in un lavoro cartaceo, ma in una sequenza estremamente dettagliata di centinaia di fotogrammi dove si vede l'aumentare punto per punto della figura di interferenza con un impatto psicologico e emotivo estremamente diverso che non guardare una figura fissa in un lavoro.
Un'altra cosa di cui ci siamo resi conto, se non altro, era che l'esperienza era estremamente bella e affascinante e si inseriva da un punto di vista proprio di importanza didattica in quel filone dei film del PSSC che allora andava tanto di moda e che rappresentano, a mio parere, a tutt'oggi dei classici della divulgazione didattica.
Volevamo fare un film di lunghezza dell'ordine dei 20-25, mezz'ora massima, perché potesse essere utilizzato durante un'ora di lezione per presentare la problematica e avere un minimo di tempo per parlarne oralmente e nello stesso tempo perché la crescita della figura di interferenza era una cosa così toccante, così da un punto di vista espressivo convincente che ritenemmo fosse una soluzione unica.
Inviammo il film a Bruxelles senza neppure essere presenti sul posto, ci raggiunse una telefonata dall'ambasciata d'Italia: avete vinto il primo premio, medaglia d'oro.
A quasi 40 anni di distanza dalla realizzazione, l'esperimento e il film mantengono intatta la loro attualità come strumenti didattici e divulgativi per introdurre studenti universitari e di scuola media superiore nel mondo affascinante della fisica quantistica.
Devo dire che, sarà per il fatto che ho contribuito, non mi ha mai stancato. È un film che potrei classificare molto, con un po' di esagerazione, ma una specie di evergreen.
Okay, so the initial part of the movie has the link to the single part of the experiment. So I will put it into the material that is uploaded into Virtuale. So now I shall try to change the screen in order to start again with the class. Okay, now you should be able to see the page again of the slides. And you may remember that during the last couple of lessons, we have listed a number of experiments for which in some cases a partial explanation has been given. And some other experiments were not explained yet during the presentation. Now we start with the first attempt of putting all these things together and illustrate what goes under the name of Bohr hypothesis. That was issued in 1913. Okay, you may remember that the emission of radiation from excited atoms is described by the Balmer law that indicates that the frequency of the emitted radiation is given by a formula in which two integer numbers appear. Now, the issue is that from another reasoning, that one that comes from the interpretation of the photoelectric effect, the hypothesis is that the energy of the photon is given by the product of its frequency by the Planck constant. So the idea is, why don't we multiply both sides of Balmer's law by the Planck constants? So if we do so, we obtain this formula in which the left-hand side, h-ni with the two indices, is at this point the energy of the photon that is emitted by the atom during the decay. The right-hand side contains the two integers, and we may split it as the difference of two negative quantities. One is minus h-ni sub r over m squared, and the other is minus h-ni sub r over n squared. If you remember, the integer m is strictly larger than the integer n. That means that the modulus of the first quantity in parentheses is smaller than the modulus of the second quantity in parentheses. That means that the energy h minus h-ni r over m squared is negative because of the minus, but is less negative than the other one. So the first parenthesis is larger than the second parenthesis. So one may interpret this formula by saying h-ni is the energy of the emitted photon. The emission of this photon is relative to the decay of the atom from a larger energy to a smaller energy. So we may say that the first parenthesis is the larger energy, minus h-ni sub r over m squared, and the other one is the energy of the lower state. Why are these energies negative? Well, you remember that we always consider an electron that is bound to the atom. So remember in the diagrams that we illustrated at the time of studying the planetary model, if we place the zero of the potential energy to infinity, then the total energy of the bound electron is negative, okay? So this formula, the Balmer formula, can be interpreted as an energy balance equation, okay? So we can simply introduce new symbols. You see it here. We can call the first energy E sub m and the second energy E sub n. Both are negative, but E sub n is more negative than E sub m. And we interpret E sub m as the energy of the atom, that is the energy of the electron, actually, before emitting the photon, and E sub n, the energy of the electron after emitting the photon. In this way, we have transformed the Balmer law into the expression of energy conservation. The energy of the emitted photon is equal to the loss of energy by the atom during the emission. Okay. Using this interpretation, we can also interpret another rule that we did not discuss before, is the so-called emission rule of Ritz, that also links the frequencies of the emitted radiation. Sometimes it was found that instead of emitting one radiation, the atom was emitting two radiations at lower frequencies, one after the other. And if the two frequencies are some ni of two indices nk and ni of two indices km, the experiments showed that the sum of these two frequencies is actually equal to the frequency that would be present if the radiation were emitted altogether. This is not easy to explain as long as we think of frequencies, but if we think of energies, this is obvious. It may happen that the transition from the larger energy E sub m to the smaller energy E sub n is made in two steps, going from E sub m to some intermediate value of energy, E sub k, and then performing the second step, going from E sub k into E sub n. Okay. If we follow the hypothesis by Bohr, then we must conclude that number one, the variation of the energy of the atoms that interact with the radiation are due to the electrons. This is reasonable because it is easily understood that it is very likely that the external electron of an atom more easily interacts with the external radiation, so it changes its orbit, so to speak. The second part of the hypothesis is a little bit more difficult to digest. It is that if there is a situation with no radiation around, so the atom is not absorbing and nor emitting any radiation, so its energy does not change, we must admit that the energy of the non-radiative state is quantized. That is, it is described by an integer index, okay? That means that the other energies that are not described by this formula, that is the energies that belongs to the interval between n and n plus 1 or n and n minus 1, okay, we must admit that these intermediate energies are not allowed, that the only allowed energy states are those described through the integers by this formula. And finally, if there is a perturbation such that the total energy of the electron changes, this change may occur only between the quantized values, that is, the values indicated by two integers. And this variation of energy, if the energy of the electron increases, that may happen by absorbing a photon whose energy is related, whose frequency, sorry, is related to the energy of the two states involved by the formula that you see on the screen, Em minus En divided by H. Or conversely, if there is an emission, the frequency of the emitted photon is still given by this formula. And these are still hypotheses, okay? They are correct because they are consistent with the experiments, but they still do not form a general theory describing all the aspects of these experiments. Now there is an interesting point. Let's accept the quantization of energy. So that let's accept that the energy is described by a formula like, for instance, this one, E sub m equal to minus h ni sub r over m squared. And then we ask the question, what happens to all the remaining dynamical quantities? If we quantized energy, should we quantize velocity, momentum, position, radius of the orbit, and so and so? We may try, because we may simply go back to the planetary model. The planetary model, as you remember, provided all the possible relations between energy, radius, momentum, or velocity of the electron. And then we replace the expression of the energy depending on the integer index, and we shall see what happens, okay? So we are simply applying, again, the formulas of the planetary model, introducing the quantization of energy. You remember that if there is no external perturbation, the total energy is conserved. It is given by the sum of the potential, the kinetic plus potential energy. But in the planetary model with the circular orbit, we demonstrated easily that the kinetic energy is equal to minus 1/2 of the potential energy. The potential energy is negative, you remember. So that on one side, we can write that the total energy is equal to 1/2 the potential energy, but then we remember that the potential energy depends on the orbit's radius as 1 over r. So we simply replace the expression of V, and what we obtain is minus q squared divided by 8 pi times the permittivity of vacuum times the radius of the orbit. So this is a relation between the energy, the total energy, and the radius of the orbit. So when we invert this relation, we find R as function of energy. Then at this point, we remember that energy is quantized due to the Bohr hypothesis. So we replace the expression of the energy, and we obtain that the radius of the orbit is also quantized. It goes with the square of the same index that appeared in the expression of energy. Okay, we can easily check if this result makes sense, because you remember that the minimum value of the index is 1. Okay, that means that if this picture is correct, the minimum radius of the orbit should be obtained with by putting n equal to 1. Okay, if we put n equal to 1 and then we replaced all the values of the constants that are present in the formula, and then maybe we obtain 10 kilometers as the minimum radius, we may think that something is going wrong. Okay, actually we don't obtain 10 kilometers, we obtain half an angstrom. And half an angstrom for the minimum radius is consistent with the measurements of the radius of the atom that can be obtained by independent experiments. So at least we obtain that the minimum radius of the atom that we obtain by this reasoning is not inconsistent with the experiments. Okay, so we are encouraged to proceed with this analysis. Then we can also try to find the velocity or the modulus of the velocity of the electron. By the same formula, you remember that the kinetic energy is equal to minus 1/2 of the potential energy, that is equivalent to minus E. And the kinetic energy, of course, is 1/2 the electron mass times the square of the velocity. So we put it equal to minus E with some index n, and you obtain a formula in which the velocity is connected with the index again. So we have quantized the velocity. So in that case, we can extract u squared, then we take the square root, and we obtain that the velocity can be written as the square root of 2h n sub r divided by the electron mass m. Okay, in this case, unfortunately, we have the symbol m that in this slide indicates the electron mass, not anymore an index, and then we have n squared. Okay. We may face a problem at this point that we don't know a priori in this analysis whether the electron has a velocity that is small with respect to the speed of light or not. If the velocity is small with respect to the speed of light, then we know that we can avoid using the formulas of special relativity in the analysis. If, on the contrary, the velocity is non-negligible with respect to the speed of light, then we must use the relativistic expressions. That would be annoying. So what we can do is we take the formula for the velocity and we consider the worst possible case. So we try to maximize the value of the velocity. And in doing that, we must take the minimum index, so we put n equal to 1, but also the minimum mass. You remember that in relativity, the mass depends on the velocity and increases when the velocity of the particle increases. So in order to have the minimum mass, we take the so-called rest mass of the electron that we call m0, okay? So if we replace m with m0, the rest mass of the electron, and n with 1, we obtain the maximum possible velocity that we call u1, and this velocity turns out to be less than 1% than the speed of light. So we are sure that we can continue the analysis without using the formula of the special relativity. We can use the non-relativistic dynamics in the following. So we stop now for 10 minutes and we shall continue at about 10:10. Okay, so we'll start and complete this part of on quantization. We have examined the quantization of the radius of the orbit and also the quantization of the velocity of the electron around the orbit. Finally, we can apply these results to quantize the angular momentum. For the circular orbit, the angular momentum is simply the product of the two moduli of the radius r and of the linear momentum p, so that we have r times the mass times the velocity, and for the mass, as you remember, we use the rest mass of the electron. Then we simply replace to r the expression of r that depends on the index that we have found initially at the beginning of this slide. And we replace to the velocity again the quantized expression of the velocity. So we found a formula that looks complicated, but several parameters cancel each other. So eventually we can express the quantized form of the angular momentum as 1 over 2 pi. Then we have the integer index n that, as usual, starts from 1 and then goes to 2, 3, and so. And then we have a quantity that is the quantity inside the brackets. And as you can notice, this quantity is made of universal constants because there is the electron charge, the permittivity of vacuum, the rest mass of the electron, the frequency ni sub r that appears in the Balmer law, and the Planck constant, okay? So if we insert the values of these universal constants into the brackets, we eventually find that the bracket is equal to h. So simply we find that the angular momentum multiplied by 2 pi is equal to an integer times the Planck constant. Okay, very simple formula. We also deduce from this result that since the quantity in brackets is a combination of universal constants, and this combination provides again a universal constant that is not a new one, it's one of those that appear in brackets, okay? The conclusion is that the universal constants that are in the formula in brackets are not independent from each other. We may conclude that one of them can be expressed in terms of the other universal constant. So the conclusion is that it turns out that ni sub r is not to be considered a universal constant. Ni sub r is a function, is a constant that is a function of the other fundamental universal constants that are Q, epsilon 0, the electron mass, and the Planck constant, okay? So ni sub r is not independent, is a product, is a combination of the others. So the conclusion is, yes, we can quantize the dynamic properties of the atom in this very simple still used in the planetary model in this very simple picture. And the results are not contradictory, okay? They seem reasonable, okay? So we continue on this line and we introduce some other improvement in the theory, because the Paul hypothesis, okay, describes well some aspects, but is not able to account for some other phenomena. You remember that the electromagnetic theory tells you that if you have a charged particle that is subjected to an acceleration, this particle must radiate. And, sorry. And apparently, instead, an electron that belongs to a quantized energy level does not radiate, okay? This energy does not change unless there is an external perturbation, okay? So this is not explained by the Bohr hypothesis, okay? Another thing that is experimentally observed is that the excited states, that is the states of the electron in which the energy has an index larger than 1, are actually unstable. If the electron absorbs energy from outside and goes to a higher energy state, then after some time it decays to the ground level, that is the level corresponding to the index n equal to 1, without any external perturbation. The decay is spontaneous, okay? So these things are not explained by the Bohr hypothesis. The only experimental fact that is found is that the ground level E sub 1 is stable. If there is no perturbation, the electron never leaves the state. And the other thing that is yet to be explained is that the orbits, electrons that are in the quantized states do not radiate energy. Now we have to introduce another hypothesis, and this hypothesis is due to de Broglie, and it was made in 1924, okay? And the idea is the following. If we have a physical process that is quantized, essentially we have a process that is described by integers. Properties that are described by integers are reminiscent of sorry, I have a message in which a student says that the slides are not visible. I do it. Can you send me a message to check whether you see the slide entitled the de Broglie hypothesis? Do you see it? Okay, so the idea is that if there is an integer index, this index is reminiscent of what we call in the solution of equations we call an eigenvalue. You remember in mathematics we have the eigenvalue equations in which the solutions are associated to integer indices. And typically, the eigenvalue equations are associated to oscillatory processes or undulatory processes, okay? So the idea by de Broglie was trying to associate a function to the motion of particles that is associated to that is describing an undulatory process, okay? This function was called by de Broglie wave function. It is universally indicated with the letter psi, and in general it is made to depend on the position and on time, okay? For the moment we are just introducing this function without trying to provide this function with any physical meaning. It is just for the moment a function that is associated to the dynamics of the particle and should be able to justify the quantization, okay? So if you still think of the orbiting electron and you want to associate a periodic function to an orbiting electron, what you could do is associate a periodic function such that if lambda is a period, for the moment let's call it a period, okay? It looks like a wavelength, but it is a period of the periodic function. If we multiply this period by an integer, we should find the total length of the orbit. This is visible in the figure that is in the next page, so I'll go back to this page soon, but for the moment I just want to show you this figure. Let me make it smaller. You see with the thin line, there is the circular orbit of the electron with the radius r. And the thick line is some undulatory function that we know nothing about. But in order to be associated to the orbit, of course, the number of periods should fit exactly the length of the orbit. Okay, so you see the length of a single period lambda, that is the wavelength, of course, of this function, is marked in the figure. And an integer number of such periods should be able to be equal to the length of the orbit. In this way, we have quantization, okay? Some of you may argue that the wavelength can be introduced exactly only in the case in which the propagation is rectilinear, okay? We cannot formally define a wavelength over a circular orbit, but if we consider a case in which the number of wavelengths that are present in the problem is very large, so that the wavelength is much, much smaller than the radius of the orbit, in this case, approximately we can think of the wave as practically planar, okay? So the wavelength is well defined, okay? So we have introduced a wave function without telling what the physical meaning of it is, okay? It is simply, for the moment, a function that is associated to the dynamical motion of the particle and tries to associate an undulatory process to the mechanical motion of the particle. Now, in order to proceed, what we could do is, let's take the simplest possible case. That is, we take the simplest possible case in mechanics, and the simplest possible case of a motion in mechanics is the linear uniform motion of a particle. That is, a particle that moves at constant speed in vacuum. And then let's try to associate to the simplest mechanical motion the simplest undulatory process, okay? And of course, the simplest undulatory process is the planar and monochromatic wave. So this is a postulate. We say if we want to associate an undulatory function to a mechanical motion, well, let's try to associate the simplest undulatory function to the simplest mechanical motion. And since the simplest undulatory function is the planar and monochromatic wave, we postulate that the form of psi to be associated to the linear uniform motion of a particle is the one that is indicated in the formula. You see that in order to have a planar monochromatic wave, it is essential that the argument of the function has the form that is indicated there. So it depends on position and time according to the expression k dot r minus omega t, in which omega is the angular frequency of the wave and k is the wave vector. The reason why we consider the complex form is not fundamental. Simply, the complex form of the wave function is more easy to manipulate. In any case, we can always reduce the analysis to the analysis of real function, but the complex form is more easily dealt with, okay? A is some constant that may also be complex, okay? And you also remember that when a function depends on the argument in this way, the wave vector k provides the direction of the particle motion. So the particle moves along the wave vector k, that is also the vector that is normal to the planes of equal phase of function psi, okay? Now, we have two parameters here, and the two parameters are the angular frequency and the wave vector k, okay? The constant is not a parameter. The constant is something that for the moment we take as is without discussing it, okay? So the actual parameters in this wave function are two, omega and k, okay? And now the de Broglie hypothesis comes. And the hypothesis is the following. You remember that at some point we have discussed about the photon. We have introduced the concept of photon. That is, the photon is a particle by which we describe the electromagnetic field. Okay, so we start with an oscillatory or undulatory phenomenon, that is the electromagnetic field, and we superimpose to it a description by particles. At that point, we must, when we discussed about photons, we had to give these particles an energy and a momentum, okay? These particles are traveling in vacuum. They must have energy and must have momentum. And we did it. We associated the energy of the photon to the frequency. We said, given the frequency of the electromagnetic mode, we find the energy of the photon by multiplying the frequency by h. And we also found the momentum, okay? The momentum was associated to the wavelength by the expression momentum p equal to h divided by the wavelength lambda, okay? So for the electromagnetic field, we started from the undulatory processes given by the Maxwell equations, and we ended up with the mechanical description in terms of particles. We had frequency and wavelength. From them, we introduced energy and momentum of the photon. What we had to do now is the opposite. We have a mechanical particle as a starting point. We want to introduce an undulatory process associated to it. That is a description in terms of waves. We start with the particle. The particle, we are considering the linear uniform motion, so we completely describe the particle by means of total energy and momentum, okay? And we have to define the angular frequency omega and the wave vector k of the oscillatory function associated to the mechanical motion. Now, the postulate by de Broglie is the relations by which we associate omega and k to energy and momentum of the particle are the same as for the photons, simply written in reverse. We start from the mechanical quantities, we end up with the oscillatory quantities, okay? Conclusion, it is written in the simple relations that you see here. You remember that the modulus of the wave vector is 2 pi over lambda, where lambda is the wavelength. So if we follow this pattern, we must say that omega is equal to 2 pi frequency. This is trivial. At this point, we take the energy of the mechanical motion of the particle E, and we, by postulate, impose that the frequency must be equal to energy divided by h. Or conversely, since we have 2 pi over h, we can write E divided by h bar. So this sets up the calculation of omega in the expression of the wave function. It is energy of the particle divided by h bar. Then we have momentum. But you remember k, the wave vector is 2 pi over lambda. This is trivial. But now we impose the same relation as for the photon. So we write lambda equal to h divided by p. P is the mechanical momentum of the particle. Again, we have h over 2 pi, so we have p divided by h bar. This is for the modules. Then we convert it into the vector form, and we have the vector k is equal to p over h bar. Okay, so this line is simply replicating the same expressions that we had for the photons in reverse order. We start from the mechanical quantities and we end up with the oscillatory quantities to be introduced into the wave function. Okay. You may have a doubt that this wave function is something of electromagnetic type. It has nothing to do with the electromagnetism. The wave function is something that is associated to the mechanical motion. It is not a part of the Maxwell equation at all. Okay. And this can be immediately verified because if you still consider the linear uniform motion, the total energy is purely kinetic. So the total energy can be written as energy equal to the square of momentum divided by twice the mass, E equal to pi square over 2m, okay? Now, if you replace term by term, E with h bar omega, and P with h bar k, you obtain that after some simplification, omega is equal to h bar over 2m k squared. So omega is quadratic with respect to k, which is typical of mechanical problems. Energy is quadratic with respect to momentum, okay? If you consider the electromagnetic theory instead, you remember that for the electromagnetic waves, the angular frequency is equal to the speed of light times k. So for the electromagnetic case, the angular frequency is proportional to k, whereas for mechanical particles, the angular frequency of the wave function is for the free particle is proportional to the square of k. You can also compare the de Broglie hypothesis, in which we assume that this relation applies, that is an integer number of wavelength fills exactly the orbit, okay? You can compare this relation with the quantization of the angular momentum that we derived from the Bohr hypothesis. You remember, from the Bohr hypothesis, we derived a 2 pi Rp, that is the Rp is the angular momentum, is an integer number of h, okay? If you take the formula above, 2 pi r equal to n times lambda, and you multiply it by p, okay, then of course p times lambda is h, and this formula becomes identical to the Bohr quantization condition. So you see that at least the hypothesis by de Broglie is not inconsistent with the quantization condition of Bohr. So we did not find any inconsistency for the moment in this new part of the theory. Of course, we don't know what the wave function is, okay? We simply introduce the wave function as an oscillatory complement of the mechanical motion. Obviously, this is nice, but is insufficient, because if this association of the planar monochromatic wave is correct, it applies only to the uniform motion of a particle. But in the majority of cases, the particles do not have a linear uniform motion. The motion is more complicated. So we may try to extend the theory a little bit by assuming a different case. We assume that the dynamics of the particle is such that the particle's motion is not uniform, but the dynamics is conservative. Okay, what does it mean? It means that the wave function cannot have a term of the form exponential of j k dot r anymore, because in this case the k vector identifies the direction of the particle motion, and in this formula k is a constant. Okay, so the space part of the wave function is not correct anymore if we consider a more general type of motion. But the time part, the exponential of minus omega t, may stay, because if the motion is conservative, and for the moment we consider only a conservative motion, then the total energy is conserved. So there is one single constant omega that is equal to the total energy divided by h bar. So the idea is, if we want to extend this description using the wave function to describe a motion of the particle that is more complicated than the linear motion, so such that there are external forces acting on the particle, but the total energy is a constant, we may consider a generalization of the wave function in this form. And let me find it. The generalization is here. So the new wave function that is able to describe a conservative situation is the product of another function w that depends on position times the time factor exponential of minus j omega t. So in this case, the total energy of the particle is still given by h bar omega. So it is a constant and the total energy is conserved. Instead, the other factor, WR, that we call the space or the spatial part of the wave function, is some function of position that is not anymore the simple exponential that appeared in the planar and monochromatic case. Okay, so this function W must reduce to a times exponential of j k dot r for the linear uniform motion. Okay, so this is the form of the wave function for the conservative case. It is still monochromatic because there is only one omega, okay? But it is not planar anymore. And this function W, the space part of the wave function, becomes an unknown function to be found, okay? It is intuitive that in order to find a function, we need an equation that is a differential equation whose solution provides us with the space part W of the wave function. Okay, so now the problem is how to find the equation from which we derive W. And now we are back to the experiment. Okay, you remember that during the description or the initial description of the movie, I mentioned the Davison and Gellner experiment. Okay, and the Davison and Gellner experiment, that was completely different from the two-slit experiment, and we shall see it in a second. Okay, was carried out in 1926, and it is a very curious experiment indeed. So let me turn to the slides. Okay, so let me change the screen. Okay, now you should be able to see a figure. And this figure shows the original experiment by Davison and Gellner. The idea was to measure how electrons bounce back from a target. So the experiment is like this. There is a vacuum vessel made of glass, and inside the vessel there is, as you see in the upper part, there is a filament. The filament is attached to the battery. The battery is the one above the filament, so that the current that goes through the filament heats up the filament, and the filament emits electrons, okay? Of course, these electrons would stay in the vicinity of the filament and eventually go back into it, but there is another battery that you can see that is attached between the filament and the other thing that is called the plate. Okay, so the plate is made positive with respect to the filament. So as soon as one electron is emitted by the filament, it is attracted to the plate, and the plate has a little hole in it. So the electrons that are able to cross through the hole, all of them have the same direction. Okay, so all these electrons have the same direction and also practically the same energy, because the energy is the energy that they acquire from the accelerating voltage applied to them. So it is the product of the accelerating voltage times the electron charge. Okay. So these electrons are oriented onto a target, and the target in the experiment was made of nickel. And these electrons, then they bounce back from the target. And in the vessel, there is also a detector. And the detector can move according to angle phi that is visible in the figure. So the position of the detector can be changed, and the idea of the experiment was to measure how many electrons were deflected depending on the angle phi. Okay, so to provide a measure of the dependence on phi of the fraction of the detected electrons. Okay. The nickel target had no special structure. Okay, it was more or less amorphous. Okay, and the experiment went along for a few days, and there is a curiosity about it that one evening Davison and Germer removed the nickel target from the vessel and put it on the table, and then they left. Later on, somebody came into the laboratory to clean up the laboratory. And during the cleaning, the person that was cleaning the laboratory hit a bottle of acid, and this acid spilled onto the nickel target. And because of that, there was a chemical reaction that covered the surface of the nickel target with the product of this reaction. So essentially, the nickel target was destroyed. When Davison and Germer came back the next morning, they found that the nickel target was destroyed, and they did not have any other nickel target to continue the experiments. So they had an idea. They had the idea of putting the nickel target to a very high temperature, so that the coating that was the result of the chemical reaction would evaporate, and eventually they would have the nickel target back available for the experiments. And actually this was successful. The coating evaporated, but in the increase in temperature of the target was so high that essentially the target recrystallized, so it became crystalline. On becoming crystalline, it became periodic, and a periodic structure acts similarly as many slits, one after the other. Okay, so this periodicity of the nickel target that was not present until the day before changed completely the outcome of the experiment, and this is visible in the next slide. So now you should see a diagram in which the the dots show the intensity of the scattered electrons depending on the measuring angle. Okay, so you see that there are angles like that at 50 degrees in which the majority of the electrons are scattered. So they bounce from the nickel target into preferential orientations. Okay. Then, of course, there will be another peak somewhere else, but in this case, the experiment was able to find essentially that at 50 degrees there was the majority of the scattered electrons. And this is reminiscent of quantization. Okay, you have a number of peaks. Okay, so this is the true story of the Davison and Germer experiment. They never had two slits because they didn't think of it, okay, and it was not anyhow possible at that time to perform the experiment in that way, okay. The modern experiment can be described schematically in the way that is shown in the next slide. So this is the typical figure that you find in books. It is also purely theoretical, okay? But essentially it says, consider a screen with two slits, 1 and 2, okay? And then you launch electrons from the left against the screen, and all these electrons have the same energy and the same momentum, so they are all parallel to each other, but you launch them one by one. So these electrons do not interfere with each other. If then you block one of the two slits, like slit number 1, okay, only the electrons that happen to cross slit number 2 can proceed, and they will eventually reach the screen that is on the right. Obviously, some of these electrons, in going through the slit, will suffer some lateral deviation. So not all of them will be aligned with the slit, but some of them will go left or right, or in this figure, up or down, okay? So eventually what we find is a distribution of electrons that has a peak, and the peak is in the position aligned with the slit, and then you have a decrease in number of electrons as you go away from the position of the peak. If you, of course, block slit number 2 and keep slit number 1 open, of course, you find the same thing, simply shifted downwards. Okay, so this is what you expect if you keep one slit open at the time. Okay. Now we are at the end of the hour, so we stop for 10 minutes and we shall proceed with this ideal experiment in the next hour. Okay, so let's continue with the description of the ideal experiment with the two slits. We already described what one would expect by considering one slit at a time. And now we change the view and consider the case in which both slits are kept open. So now you should see another picture in which both slits are open in a situation in which the particles are behaving classically. What one would expect by opening the two slits together would be a superposition of the two peaks that were present in the previous figure. Okay, so in a purely classical situation, one would expect a superposition of the two peaks. So if you look at the central part of the figure, you see the two peaks independently. And if you look at the right part of the figure, there is one curve that I'm now describing with the mouse, that is the superposition of the two peaks. Okay? And this is what one finds if in dealing with particles that have big masses. Okay, so when you can apply, when you are dealing with microscopic particles like electrons, instead, you don't find the superposition of the two peaks, but you find an interference pattern. So the counting of the positions in which the electrons hit the screen on the right has a shape that is of the type that I'm now following with the mouse. Okay, so it is an interference pattern. And if you apply the same type of calculation that can be applied when considering the interference of the electromagnetic waves, okay, you remember that from some geometrical features of the diffraction pattern, like the distance between the two peaks, two consecutive peaks, one can deduce some properties of the radiation, for instance, the wavelength of the radiation, okay? And this is the same for the electrons, okay? Again, this is an ideal experiment, okay? The true experiment with the two slits that was done, that was described in the, whose preparation was described in the movie that I showed initially, gives you something of this type, okay? So now you should be able to see a number of shots indicated with the letters A to F. And you remember, we launch one electron at a time. So one electron hits the screen, and for instance, screen number A shows what happens after just one single electron has been launched, okay? The screen is a film that records the position in which the electron hits the screen itself, okay? So the white dot is the position where the first electron has hit the screen, okay? Then you keep launching the electrons. You have something like case B. So case B is after launching, say, 10 electrons, okay? And there is no visible pattern, okay? So it looks like the electrons land on the screen in random positions, okay? Then you keep launching electrons, let's say 100, you have the situation of screen C, okay? Still you don't see that much, okay? But after 1000, if you go to case D, you see that the majority of the electrons land on the screen in a specific pattern. They are aligned, okay? And this is even more visible in screen E and even more in screen F, okay? So eventually screen F shows that the combination of many electrons actually does provide an interference pattern on the screen, okay? But this pattern is the result of the construction of the landing of many electrons, okay? And each of them had a specific position on the screen. And from the distance between the peaks of this pattern, one can reconstruct a wavelength, and using the de Broglie relation, one can also extract the momentum of the electrons and compare the momentum of the electrons with the momentum of the electrons that were originally launched by the equipment, and find that this is exactly the true momentum with which the electrons were launched, okay? When the electrons are launched, they are free particles, so the momentum is uniquely related to the total energy, so it is a known parameter of the experiment, okay? Now, the outcome of this experiment is very important because it provides us with the possible physical interpretation of the wave function, okay? For the moment, you remember the wave function is simply a mathematical symbol attached to the mechanical motion of the electron, okay? The idea is maybe the wave function can be exploited to find out the statistical distribution of the electrons of this experiment, okay? So in this experiment, we have obviously a conservative motion, okay? The electrons may suffer some deviation when they cross the slits, okay? So they have a distribution, but there is also an interference of the electrons built up in the experiment, and possibly the wave function can be exploited in order to deduce the statistical distribution of the electrons of the experiments, and more generally the statistical distribution of the electrons when we describe a possible mechanical motion of the electrons themselves. If we accept this view, we must also consider the fact that when we consider a statistical distribution, we are dealing with many particles. Okay? So now I'm going to show again one of the previous figures, those of the ideal experiment, this one. And let's assume that the wave function is able to provide us with the information about this interference pattern, that is the statistical distribution of the electrons on the screen, right after the electrons have hit the screen. Okay? If this is possible, the same function should also be able to provide us with the statistical distribution of the electrons just before hitting the screen. Okay? So the idea is this function should be able to provide us with the information of the statistical distribution of the electrons in space. Okay? Now let me try to resume the slides. You should be able now to see a slide that is entitled Statistical Interpretation of the Wave Function. Okay. So, as I mentioned before, we interpret the Davison and Germer, or the modern equivalent experiment, equivalent to that of Davison and Germer, to extract the wavelength associated to the motion of the electrons from the distance between the interference fringes. And actually we do it, okay? So if we try to do so, we find the correct momentum and energy of the electrons. Now we assume that the wave function is able to provide the distribution of the electrons on the screen. That distribution is measured by the intensity of the fringes, okay? When the fringes are more intense, we have more electrons that have hit the screen in that position, okay? But this is equivalent to describing the number of electrons that just before hitting the screen are in a little volume near the screen. Okay. So this little volume is some little volume that we call tau, whose sides are delta x, delta y on the screen, and delta z normal to the screen. Okay, so the wave function should be able to provide the information of how many electrons are present in that volume. Okay. On the other hand, the wave function is complex. So we cannot just say the wave function in itself gives such a number, because this number must be a real number, okay? So there must be some function that depends on the wave function and is also real, such that it provides this number, okay? So we consider a small volume that is not elementary, it is finite, it is tau, it's a finite volume, okay? And we seek for a function of psi that we call F for the moment, such that its integral over the small volume predicts the number of electrons, okay? Now, how can we deduce this function F that is a real function depending on the wave function? We have different possibilities. One is simply the repetition of experiments and the observation of experiments. Another possibility to find this function F is to resort to the analogy with the electromagnetic case that was also helpful. You remember when we used the association of the mechanical and electromagnetic properties or undulatory properties that were present in the electromagnetic field for the photons, okay? When we consider the electromagnetic field, the basic quantities are the electric field and the magnetic field. But then we have also something that is the intensity of the radiation, and the intensity of the radiation is the square modulus, is associated to the square modulus of the electromagnetic field, okay? So we may also think that also in this case, in order to describe the distribution of the intensity of the electrons on the screen, we should use the square modulus of the wave function. So, and this is actually true. It is corroborated by experiments. So what we should use is the square modulus of the wave function. That, of course, is a real quantity, okay? And this square modulus, after being integrated over a small volume, provides the number of electrons that belong to that volume at time t, because you remember that the wave function also depends on time, if we made a measurement of this number of electrons in that volume, okay? So the statistic interpretation of the wave function is this. We take the wave function at some instant of time, we take the square modulus, we integrate that square modulus over a volume. This gives you a number. This number is the number of particles that belong to that volume at time t. This is the statistical interpretation of the wave function that is due to Born, not Born, okay? This also shows that the units of psi modulus squared are those of the inverse of the volume, because the square modulus of psi times volume d tau is a number. So the modulus squared of the wave function is as the units of the inverse of a volume. Okay. That also indicates that the wave function by itself has the units of length to the minus 3/2. Okay. Now the issue is this description of the dynamics of the electrons based on the wave function that in the Born interpretation works when you have many particles and then we calculate the statistics over them, okay? It should also work when we consider one single particles, okay? In fact, you remember that when we started considering the wave function, we introduced the wave function as associated to the motion of a single particle, okay? So now we have to move from the statistical interpretation of the wave function that deals with many identical particles to the so-called probabilistic interpretation of the wave function still due to Born, okay? And this interpretation is very simple. You remember when you go from statistic to probability, what you say is that the integral, when you consider one single particle, the integral of the square modulus of the wave function at an instant of time t integrated over the volume is proportional to the probability that if you measure the position of that particle, you find the particle within volume tau at time t, okay? This is the probabilistic interpretation. The square modulus of psi integrated over the volume is the probability to find the particle inside the volume. This probability must be understood as a priori probability without measuring, because if you measure, either you find the particle or not. At that point, you are sure whether the particle is in the volume or not. So it is a priori, without measuring, okay? Why do we say proportional to the probability instead of saying equal to the probability? Because now we must see what happens when we extend the volume to infinity, okay? If you extend the volume to infinity, you expect that the probability should become equal to 1, because if you have, if that particle exists somewhere, and you consider the whole infinity as a volume, of course you must find the particle somewhere. So you expect that this particle, when you integrate the wave function over infinity, you find a probability equal to 1, okay? But the point is that there are wave functions whose integral over infinity diverges, okay? And the typical example is exactly the wave function associated to the uniform motion. If we go back by a few pages, okay? If you take this function here, and you take the square modulus, the exponential, of course, gives you 1. So the square modulus is the square modulus of A. Then if you integrate this quantity over a finite volume, of course, you find something finite, okay? Which can be any number, it depends on what A is. But if you integrate this over infinity, you find infinity. So the simplest possible wave function turns out to be non-integrable in modulus, in square modulus, over the space, okay? So this is a case in which we cannot talk about probability. okay, because the integral diverges. In the majority of cases, it does not diverge, so it converges, but this is one example in which, okay, so we must say, before we let tau go to infinity, we must check whether the wave function that we are considering can be integrated in square modulus, okay? If it does, we call it normalizable, okay? If the function is normalizable, we can always multiply the function by some real constant, sigma, to obtain a new wave function that we call psi prime, whose integral over space is equal to 1. Okay, so if the function is normalizable, you can always manipulate the wave function in order to have the integral of the square modulus being equal to 1. Okay, the question is it legitimate to manipulate the wave function? Can we simply freely multiply the wave function by a constant at will? The answer is yes. We shall see immediately why. Okay. So if the wave function is normalizable, then we can renormalize it to 1. And in that case, we can say the integral is not proportional, is equal to the probability to find the particle in the volume tau. Okay. So if the wave function is normalizable, we are on the safe side. Okay. We can speak freely of probability. In the other case, in which the wave function is not normalizable, like the one describing a free particle, we can talk of a ratio of probabilities. We can integrate over volume tau1. Tau1 is finite. Then we can integrate over another volume, tau2, also finite. And then we can take the ratio of the two integrals. In this case, we can say this ratio is the ratio of the probability to find a particle inside volume tau1 and the probability to find a particle inside volume 2 tau. In any case, the number of functions that are non-normalized is limited, okay? So for the majority of the functions that we shall encounter, the normalization condition is applicable, okay? Now we have to justify the issue. Can we normalize at will the wave function if it is normalizable? That means, can we multiply it with some constant suitably chosen? The answer is yes. And the reason is this. We shall see later that the wave function is the solution of a differential equation that is homogeneous. Not only the equation is homogeneous, but also the boundary conditions are homogeneous. Okay, so this is a case in which if we find the solution of the differential equation, then any other function obtained from the solution after multiplication by a constant is still a solution. Okay, so it is legitimate to multiply the normalizable wave function by a constant because the wave function is by nature defined apart from a multiplicative constant because of homogeneity. Okay, so it is legitimate. So since we are talking about probability, we said this is what we find by using the wave function is a probability a priori. What happens if we make a measurement? Okay, so the issue is somebody has calculated for us the wave function. Okay, so we find and assume that this wave function can be normalized. So we know the probability to find the particle in some volume. Okay, so let's assume that we have a wave function that is non-zero inside some volume tau and identically equal to 0 outside this volume tau. Okay, so we know for sure that the particle is inside volume tau because the wave function is non-zero over this volume, okay, and it is 0 outside. So the probability to find the function outside tau is 0. Now let's assume that we make a measurement of the particle, of the position of the particle, and this measurement provides an information that the particle is inside a volume tau prime that is inside tau and smaller than tau. So by this measurement, we have obtained a better localization of the position of the particle, okay? Because before the measurement, the larger volume tau was the volume in which we could find the particle if we made the measurement. After measuring, the measurement has not been infinitely precise, okay? If it is infinitely precise, we find 1 point, ideally, okay? We find 1 point where the particle is. This measurement is not so precise, but enough to provide us with the information that the particle is inside tau prime, and tau prime is smaller and inside the original volume tau. Okay. From this point on, if we want to describe again the particle using a wave function, we have a new wave function that is non-zero only inside tau prime. At least is what we get immediately after the measurement, okay? Because we know that the probability to find the particle is non-zero only inside tau prime. So this wave function was non-zero outside tau just prior to the measurement, and it has become non-zero within tau prime after the measurement. That is, the domain in which the wave function is different from 0 has contracted from tau to tau prime. Okay, this is called the contraction of the wave function. There is no mystery in it. Sometimes they talk about the contraction of the wave function as an absolute mystery. There is no mystery. Before measuring, you have some information about the whereabouts of the way of the particle, okay? After measuring, you know much more because you have improved your knowledge. So there is no mystery in this contraction, okay? By the way, the duration of an experiment is never 0, okay? So the duration of experiments is finite. It takes time. Okay, so this contraction is not instantaneous. It may be considered instantaneous if we neglect the duration of the experiments. if we consider that the time scale of the experiment is much, much shorter than the standard time scale of the rest of the dynamics, okay? We already mentioned the units of the wave function. I repeat it now. If the integral of psi squared over the volume is proportional to a probability, then the square modulus of psi alone, without the differential, is a probability per unit volume. That is a probability density. Okay, so it's a density in space of a probability. For the moment, we know only one type of wave function, that is the wave function associated with a free particle, okay? And you remember that in this case, the parameter omega is associated to energy. It is energy divided by the reduced Planck constant. So given omega, we know energy. In parallel, vector k is associated to momentum. So given k is equivalent to providing the value of momentum, because k times the reduced time, the Planck constant, is momentum. Okay. So for a wave function describing a free particle, we know at the same time momentum and energy. The total energy is equivalent in this case to the kinetic energy. Okay. This is no contradiction. Okay. This is actually true also in classical mechanics. In classical mechanics, the total energy of a free particle is p squared over 2m. So if you know momentum, you know exactly also energy, because you take the square and divide by 2m. If conversely you know energy of a free particle, you know the modulus of momentum. So you miss the information about the direction of the momentum vector, but you do know the modulus of momentum, okay? So you have a full information about energy and momentum, both in the classical case and in the quantum case, okay? Now let's consider the information that you may acquire from the wave function of a free particle as regards the position of the particle. So we simply apply the recipe of quantum mechanics. We say the square modulus of the wave function is the probability density of the localization of the particle. So in this case, we have a free particle wave function. We take the square modulus, and of course, we obtain the square modulus of A. So that is a constant, okay? You remember we already met this issue. If you try to integrate this over the full space, you obtain infinity. The integral will diverge, okay? But the issue is different, that this wave function provides you with absolutely no information about position, because the probability density of localization is a constant. It's equal to A modulus squared. So that means that it is the same at any position in space. There is no dependence on space left, okay? Any point in space has the same probability that the particle is there as any other point in space, okay? So the wave function associated to the free particle has a special feature. It gives you complete, full information about momentum and consequently also energy, okay? Full information about momentum. Absolutely no information about position, okay? It is a special case, okay? Now, assume that you have performed a measurement of position and that you are able to perform an experiment of localization that is extremely precise to the point that you exactly find the position of the particle at the time in which you complete the measurement, okay? So assume that thanks to a measurement, you have found that the particle is in position R0, okay? From the mathematical viewpoint, how do you describe this? If you want to describe this with a function, you need a function that is 0 everywhere in space, apart from the point R0, because the particle has been found exactly in the location R0 and nowhere else. So the function must be 0 everywhere but in the position R0. The only possibility is a delta function, is a Dirac delta. Okay, because the Dirac delta, if we use the qualitative description of it, is 0 everywhere and infinite at R0, because it is not sufficient to have some function that is non-zero in the position R0 of the particle. You need a function that whose integral is non-zero, okay? So if you take a delta, you're sure, because delta is integrable, okay? You remember the integral of the delta over space is equal to 1, okay? But using the language of quantum mechanics, we need to integrate delta square, okay? So in order to describe the localization of the particle at position R0 at time t prime is the instant at which the measurement is completed, okay? We must use delta of R minus R0. And you see that this function also is non-normalizable because the integral must be performed on d squared, and d squared is non-normalizable, okay? This function, so to speak, gives you a full information about position because there is only one parameter in it that is R0, and R0 is the position of the particle. But there is no indication whatsoever about momentum because there is no parameter that can be traced back to momentum. There is only one parameter that is R0, okay? So in essence, we are considering two extreme cases. One extreme case is that of wave function of the free particle, in which you have a full information about momentum and as a byproduct also about energy, and no information whatsoever about position. And the other one is this delta, in which you have a full information about position and absolutely no information about momentum, okay? These two let's call delta is not a function, as you know, but let's call it function for short. These two examples of functions, this exponential and the delta, are the two extreme possibilities, okay? No information about position, full information about momentum, or no information about momentum, full information about position. All the other wave functions, as we shall see, are intermediate. They are able to provide some information about position and at the same time some information about momentum of the particle. But these two informations are incomplete. Both of them are incomplete. Okay. Another observation which at this point may look like a curiosity, but it is not a curiosity. You can observe that these two extreme cases, the imaginary exponential and the delta, they are the Fourier transform of each other. Okay, you remember that you Fourier transform the delta, you have the exponential and vice versa. This looks like a curiosity, but it is not. There is a deeper reason that we shall see later. I can understand that all of this, if some of you had never before had any relation with quantum mechanics, all of this could be confusing, okay? So in order to decrease somehow the level of confusion, we must somehow describe some features of experiments, okay? We don't have time to complete it, okay? So I just start the description of a very naive scheme of measuring positions of objects, okay? And then we shall continue on this line on Thursday, okay? So consider the case in which you want to detect the position of a bus that goes from left to right on the street, okay? And you set up a very, very naive scheme. You drop from above the bus, you drop tennis balls, okay? So T is something that we can interpret as transmitter, okay? Every second, this transmitter drops a tennis ball, and then there is a hole in the street, and there is a receiver that receives the tennis ball. Each tennis ball, one tennis ball every second, okay? And then there is some guy here that observes the tennis ball that come in, okay? At some point there is a bus passing, okay? The bus will hit the tennis ball will be thrown away. So the receiver will not get any tennis ball. And the guy that is near the receiver will write on a paper at this with a watch, okay? At this second, there was no tennis ball, okay? So in this naive way, you can tell that at the position of the receiver that you call x1, at time t1, there has been a bus crossing. Okay. Now you want to improve your measurement. You want to say, I don't want just to measure positions, I want to measure velocity. Okay. So what you do, you place another pair, transmitter and receiver, nearby, and you put, this is in position x2, okay? Not so distant from position x1. Then you place another guy, and this other guy records the instant of time in which there is no tennis ball coming. So he says, the bus has crossed position x2 at time t2, okay? As a consequence, if you take the difference x2 minus x1 and you divide it by t2 minus t1, you find the velocity. So if you then consider that x1 and x1 and x2 are close to each other, you can approximate the instant velocity with the average velocity, okay? So essentially, measuring velocity is equivalent to measuring position twice, okay? And this is it for buses, okay? So we stop and we shall try to repeat the analysis using electrons instead of buses, and then we shall see what happens. For the moment, we stop here.